This was all stuff from your basic chemistry 101 class, but I know it's probably been at least a year since you've taken that class. So the entire purpose of this first video in this series was just to refresh you and remind you on the things that you are expected to already know coming into the class so you can understand what is going to be taught in organic chemistry. You don't have to spend a lot of time on it, but if you go over this stuff just really quickly before starting your organic chemistry class, things are going to make so much more sense to you and you're going to be that much more prepared. Okay, hi everybody. So I'm trying to put together a video series of intro basics, stuff that you need to know for your organic chemistry class that is probably not going to be explained well in class. I'm sorry to have to say that, and my mom would kill me if she knew that I was saying this because she always raised me to have respect for teachers, and I do have respect for the teacher. What I have a problem with is organic chemistry is well known by the nickname the Doctor Killer class because it's systemically, intentionally taught badly to weed out pre-med students. And I personally think that is insulting and unethical thing to do because if I'm paying you to get an education, then I don't want to deal with your mind games. I want the education. But we all know reality is not fair. I can't even apologize for it because I didn't have anything to do with it, but I am sorry that it exists like that. It's sort of ridiculous because here's the secret. The most difficult thing about organic chemistry is actually learning it from the classes in universities here because across the board, across the nation, it's taught poorly. And I don't mean it against teachers. They're not actually at fault. What the problem is that the core curriculum that is mandated across the board is mandated that you have to teach it this way. So my goal in this video series is to explain it as clearly as I can and to also encourage you to not give up. Okay, so I'm done with my soapbox, but I said what I said. So just to remind y'all, you're probably on YouTube right now watching this, which is Suzanne's Tutoring on youtube.com. Please feel free to comment and request any tutorial videos that you need. Also, I do have an actual website, and it's the exact same thing as my YouTube channel. It's suzannestutoring.com. And when you're looking for me on YouTube, just look for the big red S. Okay, so as I said, we're going into the meat of the stuff of organic chemistry. We're talking about mechanisms, and the mechanisms are the reactions. I'm aiming to do this video series learning the mechanisms by the reagents. And the reagents are pretty much like, like you can think of your reagents as your second ingredient. It's the thing you add to the other thing, is the reagent. So the first rule of organic chemistry is don't panic. Don't get so overwhelmed that you end up falling behind. Get your homework done and turned in on time. Most important thing in organic chemistry class. But rule number one, no matter what you do or what goes on, don't panic. Okay, so now another reason why I have this don't panic screen up is because, okay, so I'm getting ready to show you a screen with the kinds of problems that you're going to have to be able to solve. But don't panic, okay? Just look at it. You don't have to understand it yet. Just look at it, don't panic. All right, so here we go. So this is the kind of stuff you're going to be seeing on like tests and assignments. Like this will be gone, and you have to figure out what this is. Or sometimes they'll give you the product, the final results, and expect you to work backwards and figure out what the original molecule was. Okay, but I can already feel some of you out there panicking. So wait, let me get to the next screen. Don't panic. It's okay. Don't freak out. It's honestly not as bad as you think. It's okay. Okay, so now we're back to this, and we're not going to solve these right. I'm not going to go through and do these right now. I just want you to look at this, get used to looking at something that looks like this without freaking out. And we'll solve those by the end of the video series. So here's the first problem. Remember back in the previous organic chemistry video series when I was showing you how to recognize the parent chain of carbon chains and to name the substituent? Okay, so here is 3 CH3s down here, because remember, this is the C, here's the carbon, 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 carbon. Okay, so these are the carbons, but we say CH3. Why? Because every carbon has to have 4 bonds to it. So if we're looking at this carbon and the only bond it has is the previous carbon right there, then it's going to have 3 invisible hydrogens. I mean, invisible in the drawing because we just don't draw them because it takes too long normally. So we just leave them out, but I'm drawing them in for you. It'll have 3 hydrogens to compensate for the lack of any other bonds for that carbon because carbon always needs 4, right? So now this carbon bonded to this is 1. And this carbon bonded to hydrogens 2, this carbon bonded to hydrogens 3, and this 4. So see, now the carbon has 4 bonds to it. So we just automatically, it's not usually drawn into the picture, but we always just automatically assume that the hydrogens are there. So this is a CH3, this is a CH3, and this is a CH3. Okay, and then we have this carbon right here where they all attach. And we have 1, 2, 3 bonds going to all these CH3s, and then the 4th bond for that carbon is coming up here to bond with this carbon up here. So this carbon has all 4 bonds already taken care of. So it has no hydrogens because it doesn't need any because it already has 4 bonds. And then this carbon up here is attached down here to one attachment to a carbon, and then it goes to another carbon up here. It's another CH3. So that's the second carbon. Here, this first, This is the second bond, and then it comes up here and bonds to this oxygen in this hydroxy group, this OH. So that's the third bond that this carbon has. So it needs one more to have 4 bonds, right? So we just automatically know that there's one hydrogen actually sticking out of this. So I just wanted to refresh you real quick before we move on. So that was the refresher. And let's go on to some more concepts before we actually get really deep involved into cracking this code. Let's first glaze over a couple of concepts that you need to know so you can put them all together in order for you to be able to solve stuff like this. Okay, so here is the same problem that I was just showing on the other screen. It's a little more colorful on this one. And anytime you see an OH together like that, it's called a hydroxy group, because hydro for hydrogens and oxy for oxygens, right? So OH. So that's a hydroxy group. But when you see that hydroxy group attached to a carbon chain, a hydrocarbon chain, that always means that it's going to be an alcohol, like methanol, ethanol, whatever, all the alcohols. Is just think alcohol, OH. So an alcohol always has an OH in it. Now, what I want you to do is see, normally when you're in class, you're going to be taught from the point of view of looking at this, your original molecule, which is fine, but it's not as helpful, I found personally, as if you were to look at it from the reagents perspective. And remember, the reagent is like just the thing you add to the other thing to make something new. So here's the original molecule, right? So original molecule. So whatever you're going to add to that original molecule is the reagent. And this HBr reagent, that's hydrogen bromide, this HBr will kind of tackle this molecule, and they'll wrestle, and a reaction will happen. That would be the wrestling, and they will come out with a totally new set of products. But what I want to draw your attention to, first of all, is that there's this H. See, HBr is hydrogen bromide, right? So when you have this H attached to another element like this, you have to understand that although technically hydrogen is on the top row on the very left side of the periodic table, but that is actually in the metals section. Everything else below that is a metal. Like lithium's a metal, calcium's a metal, magnesium's a metal. Those are all metals. But hydrogen, even though it's over there on the left side of the periodic table, it is actually not a metal, because hydrogen does not obey the rules. So see, that's just what I said. Hydrogen is weird. It doesn't fit into a category, but mostly a good rule of thumb is to act like it belongs to the non-metals, which is why I drew this arrow over here. Because see, this is the metals, and these are the non-metals. And if you forget which is which, just think, okay, over here on the right, just pick out a good example for you. Here's oxygen, right? Okay, I just always look over at, on the right side of the periodic table, and it's like, oh, well, here's oxygen, and that's gas, so that's a non-metal. So that means this whole cluster here are going to be non-metals. So, and now we have an ionic bond when we're dealing with these two towers, group A, right? And if you don't remember that, you can go back to my sets of videos in basic chemistry, the secrets of the periodic table. Both of these towers are considered group A. If they turn into ions, if they, turn into a form that has a charge to it, which means they either gained or lost an electron, these metals on the left, well, all the metals are on the left. These are the metals on the left. These are the metals. These metals will lose electrons. And so when they're in an ionic state, they will have a positive charge. Now, it could be one positive, which is the 1A column right here, or it could be 2 positive, which is the 2A column right here. But either way, they're going to be positive. So here's metals going to be positive ions. Over here, the non-metals are going to do the opposite. When they turn into ions and they have a charge because they're not in their normal state, that means they have gained electrons, and so therefore are negative. See, I have it written right here. This negative sign when they're ions, just when they're ions. So these non-metals are going to be negative. So in an ionic bond, it's just a matter of, okay, we got somebody, over here, let's say lithium. And lithium is in group 1A in that first column. So that means if it's an ion, it's going to have 1 positive charge. So that means it has lost 1 electron. So it's missing an electron, which is why it has a positive charge. So it goes out into the world and looks for its lost electron. Okay, and then say we have, just for example, chlorine right here. Okay, so chlorine is in 1 column back from the last column. And this is in my previous videos about the periodic table. So since it's 1 column back from the last column, then that means it's going to have a 1 negative charge when it is in its ion form. And so if this chlorine has this 1 negative charge, if it's an ion and has a negative charge, then that means it has gained 1 electron. We all clear on that? Okay, cool. So when something like lithium with a positive, 1 positive charge is looking for its missing electron, and something over here in the nonmetals, like chlorine, has a negative charge because they have too many electrons, these folks can come together and get married. And now you have lithium chloride, which has no charge. Why? Because the elements have balanced themselves out. So that is what an ionic bond is. Okay, now make sure you separate an ionic bond from a covalent bond, because when I first studied chemistry, at first I didn't really get the difference between ionic and covalent. So an ionic is like something out of the metals, and which it is turned into an ion because they lost an electron, getting married with somebody who has too many electrons from the nonmetals, right? That's ionic. Okay, but covalent is completely different. It's a completely different thing, because the thing about covalent bonds, first of all, it only happens with nonmetals. So covalent bonds are only going to happen between the elements in this little cluster right here. And that's it. Okay, so this has nothing to do with charges or being ions, losing an electron, gaining an electron. In covalent bonds, nobody's lost an electron, nobody's gained an electron, everybody is at normal state, right? Okay, so in a covalent bond, what happens is that, okay, let's say we have chloride right here. So chloride, and if you go back to my intro organic chemistry, I do a refresher on this. But chloride, and as part of group A, because remember the two towers are group A. These are both part of group A, because it starts over here, 1A, and then this column is 2A. And then we skip over that little bridge and we go over here to the rest of the A group. So this column's 3A, this column's 4A, this column's 5A. See, they're already written in. I'm just writing over them. Okay, so chlorine is in column 7. So that means chlorine is going to have 7 valence electrons. Okay, valence electrons, remember the outer shell electrons. So chlorine's going to have 7 of them. So when you remember we did the Lewis dot structures, you don't bunch them up and go 1, 2, 3, 4, 5, 6, 7. That's not how you add these. You do 1 on each of the 4 sides first, 1, 2, 3, 4. Then you go back for a second time around and finish out the rest of them. 5, 6, 7. Okay, and that might not have looked any different, but it does make a difference when you get into involved stuff, believe me. Okay, so here's chlorine, and it has 7 valence electrons. So here is this poor little empty space where a valence electron wants to go, because all of these nonmetals want to get you a total of 8 electrons, right? And that's the octet rule. Is this coming back to you now? Okay, so everybody wants to have 8 electrons. Chlorine is 7 because it is in the 7th column in group A. So it's missing this one right here out of the 8 that it wants to be an octet. Now, this has nothing to do with charge or negative or positive, nothing like that. This is a normal, not negative, not positive. It's just a neutral, zero charge element that is not lost any electrons, does not gain any electrons. It's just that they have a vacant space and they really want to fill that with an electron because they want a total of 8 electrons, right? So if chlorine gets together with, say, I don't know, iodine. I don't even know if this is a real substance. I'm just taking things off the periodic table to give you the demonstration of how this works. So if there's iodine. So iodine is also in the seventh column in group A. So that means it has 1, 2, 3, 4, 5, 6, 7 valence electrons. And so here's chlorine over here, which has 7 valence electrons. And look, chlorine has a space here that really needs to be filled by an electron. And iodine has a space here that really needs to be filled by an electron, so they can both have their octet. Okay, so what do we do with that information? Well, this chlorine's electron can bond with this iodine's electron over here. And remember, they're both missing a space that they want to fill so they can get a whole octet. So by bonding and joining their electrons together, they have now accomplished getting their octet, because once they bond to another element, then they can count that other element's electron as part of their own. So now we have chlorine with 1, 2, 3, 4, 5, 6, 7, and then 8. So now it is obeying the octet rule. It has 8 electrons. And so a chlorine iodide molecule bonded together would be like this. See, there's a bond here because there's an electron on either side. So that's 2 electrons, one from the iodide, one from chlorine. And then chlorine has all the rest of these lone pairs of electrons on her. And iodine does too, has all these lonely electron pairs on all of the other 3 sides of the atom. Okay, so now that I've showed you that, stick a pin in that and just hold it in the back of your memory for a minute, because we also need to go over this real quick. Anions and cations. So these are both ions, right? Here's the word ions and here's the word ions, if you break that down, right? So ions have gained or lost an electron or electrons, so they now have a charge. So if they gained extra electrons, however many extra electrons they have, that many units negative. However many electrons that a molecule has lost is that many numbers positive in their charge. Okay, so, and that's an ionic charge. So anion, the first one right here, anion, this is a negative ion. In contrast to that, a cation, prefix cat, a cation is going to be a positive ion charge. And if you forget which one is which, see how cation has a plus in it and anion does not have a plus in its letters. So that plus means it is positive, has a positive charge, and so therefore it's lost an electron. Okay, so continuing on with this idea of ions, anions, and cations. And remember, cat has that T in it, and the T looks like a plus. So that's how you can remember that it's the cations that are the positive charges, and the anions are negative. So I've been saying that carbon needs 4 bonds. always, right? And like when I showed you how to draw a carbon skeleton, carbon here, carbon here, carbon, 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 carbon. Okay, so right here, this carbon right here has a bond to the next carbon, but it needs 4 bonds. So since it only has this 1 bond to the next carbon, then it has 3 left to go. So we automatically know that hydrogens are there for that carbon. And just like this carbon in the middle here, this carbon has a bond to the left to this carbon, and it has a bond to the right to this carbon. So that's 2 bonds. So it has 2 more bonds that it needs. So we're going to know that this carbon has 2 hydrogens that are just not drawn in the normal carbon chain, right? So why is that the carbon needs 4 bonds? The number of valence electrons an element has is the same number as the column number that it's in. And by the way, we're talking about group A on the periodic table. So, we have the columns. So 1, 2, 3, 4, 5, 6, 7, 8 columns on the periodic table that are in group A. So whatever the column number is, how many valence electrons that element has. So carbon happens to be in the 4th column. And so that means that carbon has 4 valence electrons, right, in its outer shell. Now let's look at the periodic table and actually get a visual of this. What about let's look at oxygen right here. Okay, oxygen is in column 6. So oxygen has 6 valence electrons. 1, 2, 3, 4, 5, 6. And remember, you got to put them one around each side of the element first, and then you circle back and put any leftover electrons, double them up. So see here, I've rewritten them for you. Here's the column numbers, and here are the elements. And I put nitrogen in there as well, so we can go carbon, nitrogen, oxygen, and look at these. See, since carbon is in column number 4, it has 4 valence electrons around it. Since nitrogen is in column number 5, it has 5 valence electrons around it. And since oxygen is number 6, it has 6 valence electrons. So you get the idea. And that goes for everybody in group A over here. But now, as you can remember, when we look at carbon here, carbon has the atomic number of 6, nitrogen has the atomic number of 7, and oxygen has the atomic number of 8. So those atomic numbers tell us how many total electrons are orbiting around the nucleus of this atom. So if there are 6 electrons in carbon, why am I saying there's only 4 valence electrons in carbon? Well, here's why. Because here's like the nucleus of carbon, right? And this goes for all the elements. Their very closest, most innermost, smallest orbital around their nucleus will only have 2 electrons. Always, 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 always. Will only have 2 electrons. And then after they've filled up 2 electrons on that inner orbital, then a new orbital will be made around that for the rest of the electrons. But all these orbitals only have a total of 8 maximum electrons. Okay, the only exception is that innermost orbital that has a maximum of 2 electrons. So you start off with this innermost orbital. The orbit is so small that it will only hold 2 electrons at a time. And so then any more electrons are going to start orbiting, forming a new one. And then if that runs over, if that maxes out at 8, then it'll form another orbital around that. And if that maxes out at 8 electrons, then another one. So you get the idea. But so see, carbon has 6 total electrons, and all the elements have the innermost orbital can only hold 2 at a time. Okay, so that's the first 2 out of the 6. So that's 4 left, right? So the next orbital around carbon is going to have those 4 electrons. So you got the 2 on the inside, and then you got 4 on the valence shell. So that is a total of 6, which is where the 6 comes from. So whatever atomic number these carbons or nitrogens or oxygens or whatever any of these elements have, like see, this oxygen has 8 total electrons because its atomic number is 8, but it is in column 6 because, well, the first 2 of those 8 electrons are taken up on the innermost shell or orbit around the oxygen, and then the rest of them spill over to the next closest orbital, which is going to be oxygen's valence shell, and so that's going to take up the remaining 6. Same with nitrogen. Nitrogen's first closest shell can only hold 2 at a time, so that next valence shell and the inner shell is going to have 5, and look, it's in column 5. Now, so if you also notice that this top row, those are the penthouse suites, top floor. Okay, so the elements on the very top floor of the periodic table only have that innermost shell. And so hydrogen, look over here, hydrogen has 1 valence electron because it's in column 1. So it's just going to get that 1. Boop, done. And then helium over here on the right, helium, if you look at its atomic number, it even says helium 2. So it's only going to get 2 electrons total. So boop, boop, and that fills up the innermost orbital that you could possibly get. And so these top row, the penthouse suites elements, they only have that innermost shell, and the innermost shell only holds a maximum of 2 electrons. So the second row on the periodic table, the second row, is going to have two orbital shells around the nucleus of the elements. So let's look at this next row, the third row down here. Okay, so the third row has silicon, and silicon's atomic number is 14, and it has phosphorus, and that atomic number is 15, and it has sulfur, and that atomic number is 16. And silicon is the same as carbon. It's right beneath carbon, so it's also in group 4A. Phosphorus is right below nitrogen, so they're both in column 5A. And sulfur is right below oxygen, and they're both in column 6A. So that means since silicon is in column 4A, it's only going to have 4 electrons in its outermost valence shell. Phosphorus is in column 5A, so it's only going to have 5 electrons in its valence shell, even though, look, it has a total of 15 electrons, and silicon has a total of 14 electrons. And sulfur is in column 6, so it is going to have 6 electrons on its outermost valence shell. But now we see that they're in the third row. So that means they're going to have 3 orbitals around them that keep getting bigger the farther they go out. So it's always their outermost shell is the valence shell. So in the case of silicon everybody has that innermost shell, and it maxes out at 2. All right, so silicon has a total of 14 electrons because of its atomic number. So now we've got 2 taken care of on the innermost shell, so that's 14 minus 2. So now we have 12 to go. So a little farther out shell forms, and all the rest of these shells, as they go out, all max out at 8 electrons. It's just that innermost one that only can hold 2. All the rest max out at 8. So we got 1, 2, 3, 4, 5, 6, 7, 8. So now we had 12 left to go after the 2 was taken care of on the innermost shell. So now we put 8 on this next shell a little farther away. So now we still have 4 to go. So it maxed out at that 8. So we're forming another orbital around silicon. 1, 2, 3, 4. And so now 4 electrons are around that outermost shell, which is called the valence shell. And the electrons on that valence shell in that valence orbit are called that element's valence electrons. So we're only dealing with the valence electrons, that outermost shell, which can be found out per element by noting what column they're in. Everything in column 4 has 4 electrons in their valence shell. Everything in column 5 has 5 electrons in their valence shell. Column 6 has 6 electrons in their valence shell. It's just their valence shell is going to have, see, this top row is just going to have the innermost valence shell that holds 2 electrons, and then this is going to have, the second row is going to have a second orbital, and that's the valence shell. The third row is going to have a valence shell, which is the third orbital around it, just like silicon right there. See, we got 1, 2, 3 orbitals around it. The fourth row is going to have 4 orbitals around it, and so on. You get the idea. So that covers how many valence shells are in each of the elements. It's just whatever column they're in, okay? But how do you know how many bonds that they usually get? Because I've been saying carbon always gets 4 bonds. Well, where am I getting that information from? So you start at this ending column, column 8, and you count backwards until you get to that element's column. So for carbon, here's 1 column back, 2 columns back, 3 columns back, and 4 columns back. So 4 columns back is carbon, or anything else in that column, as a matter of fact. So 4 columns back. So 4 columns back means that these elements are going to also want 4 bonds. So just like C has 4, and it's just a coincidence, the 4 and 4, by the way. Carbon has 4 valence shell electrons, right? And it is going to want 4 bonds. Because look, this valence shell maxes out at 8 electrons, right? But carbon doesn't have a whole 8 to fill up that valence shell. It only has 4. So there's empty spaces next to each of these electrons, so their buddy can sit next to them. And carbon has no electrons to sit next to their 4 electrons. So it's going to want 4 bonds to something else. I don't know what these atoms are over here. I'm just saying anything. Or we can talk about it being hydrogens, since carbons, we automatically assume hydrogens fill up the other 4 bonds. So let's just say hydrogen. It can be anything, but it's with carbon most of the time it's hydrogen unless it's otherwise notated. So carbon has 4 hydrogens around it. So those hydrogens each have 1 electron, right? Because hydrogen is in column 1A. So each hydrogen has 1 electron, 1 electron, 1 electron, 1 electron. And those each bond with the 1 electron on all 4 sides of that carbon, right? So they bond to carbon's 4 valence electrons. So let's look at oxygen, just so you can get a better idea of what I'm talking about with a different example. Okay, so oxygen, we start at column 8 and we count backwards. 1 column, 1, 2 columns, 2. So oxygen is 2 columns back from column number 8. So 2 columns back. And oxygen itself is in column number 6, right? So we're going to go column 6. So if oxygen is in column 6, that means it has 6 valence electrons. And we don't worry about any of the other electrons. You only have to worry about the outermost valence shell electrons, which is told to you how many there are by these column numbers. That's all you have to worry about. Okay, so oxygen has 6 electrons on its valence shell, on its outermost shell, right? Because it's in column 6. Now, if you look, it has 2 empty seats for electron buddies, and there are no buddies there to take up the seats. 2 people sitting together on a roller coaster, right? But this space and this space has a vacancy. So it is going to need to bond with another atom and count their electron in their octet. So if an oxygen, I don't know, it doesn't matter what atom this is out here. I'm just going to write A for atom. And remember, every bond has 2 electrons, 1 at each end. So this atom has 1 at this end, and oxygen has 1 on the oxygen end. So now, since there's a bond there and it's bonded to other electrons, oxygen can count it. So now we have 1, 2, 3, 4, 5, 6, 7, 8. So while oxygen itself still only has 6 because it's in column 6, still only has 6 valence electrons, with the 2 bonds, it can count these 2 extra electrons from other atoms bonded to it as 2 of their valence shell electrons. So now they can complete the octet rule, filling up those buddy seats in the roller coaster, so somebody will sit next to their lonely electrons over here. And so now that I've explained it like that, do you see what I'm talking about? If you count back 1 from the very last column, count back 1 and then 2 back to wherever that element is, whatever column that element is in. So we counted back 2 columns to get to the oxygen. 2 columns. And guess how many bonds it has in order to fill its octet rule? 1, 2. So that's what I mean by if you count backwards from the last column on the periodic table, that number, however many times you have to count over the columns backwards to get to the element, that number is how many bonds they're going to want. Okay, we got just a couple more points. So here's the last couple of concepts that you need to remember in order to go into OChem and be prepared. So the second to last is electronegativity. And I'm sure you were introduced to this concept in chemistry and didn't really know how this was going to fit into anything else, but it is going to fit into a lot of things coming up in organic chemistry. And this is one of those things where it's not a difficult concept, but you just need to grasp it and feel comfortable with it so you can use it, like second nature. So electronegativity is how much the element literally sucks the neighboring electrons from the elements that it's bonded to towards itself in the molecule. So as you can see here, this is increasing electronegativity. Goes this way on the periodic table. And again, this is in my Secrets of the Periodic Table and periodic table videos in the basic chemistry playlists that I have on my website and on my YouTube channel. So increasing electronegativity means down here at the bottom left is the least electronegative element. And then you go diagonally all the way up to the top right. And we just kind of ignore this 8th column right here because the 8th column is stable. That's why they call it noble gases. So they don't really participate in any of this stuff that we're going to be talking about. So the highest, most upper right element is fluorine. And fluorine right up here is the most electronegative element. So see, it's fairly easy to figure out if you're looking at the periodic table, what is the most electronegative element and which is the least. And as I just said, being electronegative means you are going to be like a big magnet. Here's a big magnet. And it's going to magnetically attract all the electrons along a bond from the other elements that it's bonded to. Now, water is the exact same way. Water has an oxygen, and then it has a hydrogen coming off one side, hydrogen coming off the other side. And these are bonded, leaving the oxygen with 2 lone pairs, because oxygen has to have 1, 2, 3, 4, 5, 6 valence electrons, and 7, 8 octet electrons. And hydrogen each only has 1 electron to it that's being occupied in the bond to the oxygen. And so hydrogen's electrons that are being bound are much, much less electronegative. In fact, hydrogen barely has any electronegativity to it, much less electronegative than oxygen. Oxygen's way up here. Oxygen's going to win the electronegative award. And so oxygen is going to suck the electron in this hydrogen. It's going to suck it up towards itself. And same thing on this hydrogen. It's going to try to suck, just like a big vacuum or a magnet. It's going to just suck the electron from each hydrogen up towards itself, making the oxygen partially negative and each hydrogen partially positive. Okay, now one more example, and it's important to drive this point home. Remember, treat hydrogen like it behaves according to the rules of the nonmetals, because hydrogen is not a metal, even though it's over in the metal classification, over in the metal side of the towers. It's really not a metal. It doesn't behave like a metal. It behaves like a nonmetal. So it behaves like it's actually over here. Hydrogen does. So in the case of hydrochloric acid, it's just a linear molecule, because here's H, and it only has 1 electron. And chlorine has 1, 2, 3, 4, 5, 6, 7 valence electrons on it. So that leaves this side open for needing a friend. So this chlorine electron can bond with this hydrogen electron. So now chlorine still has 1, 2, 3, 4, 5, 6, 7 valence electrons, but when it bonds with the electron from the hydrogen, that gives it its 8 octet electrons. And chlorine is way more electronegative than the hydrogen. So the chlorine is going to suck that electron from the hydrogen that it's bonded with towards itself. So, and the correct icon for this is a little arrow, and then it's got a plus side kind of on the end of the arrow. So that indicates that side is going to be more positive, and the electron is going this way. And so the chlorine is going to end up with a partial negative charge, and the hydrogen is going to end up with a partial positive charge. Well, that leaves, especially in the case of things like with a hydrogen being the least electronegative thing, leaving that hydrogen partially positive, so the chlorine ends up taking that. That makes this bond very weak, because there's no planes have a war with each other anymore. Instead, all the electronegativity is all pushed over to one side. So that's just going to leave the proton. not the full hydrogen with 1 proton and 1 electron, because chlorine's stealing that electron. So it's just going to leave the hydrogen as a proton, as positive hydrogen, and it's going to leave the chlorine as kind of negative chlorine, almost. See, just partial, but it's partial enough to make this bond weak enough to where it could very easily break apart into ions. And I know these are supposed to be covalent bonds, right? And I explained the difference between ionic bond and a covalent bond. So what really is the difference? Wouldn't this be an ionic bond, a positive hydrogen and a negative chlorine? No, it's not, because the reason why hydrogen and chlorine bonded together in the first place was not because of a positive charge and a negative charge. These were not hydrogen ions bonding with a chlorine ion. Okay, that would be an ionic bond. But that's not what happens with these elements. These elements bond together as regular normal elements, not as ions. This is not a hydrogen ion. This is not a chlorine ion. This is a full zero charge, completely balanced hydrogen with 1 proton and 1 electron, just a stable configuration. Same with chlorine. This is a stable configuration of chlorine. They're not ions. There's no charge. They're just normal. And it just so happens that hydrogen has 1 electron, and it just so happens that chlorine has 7 and has an empty space. It needs an extra electron for its octet rule. So they bond together to share for its octet rule. Because, as you recall, an ionic bond would have to be an ion from the nonmetals plus an ion from the metals. But remember, I said don't count hydrogen as a metal. Count it as a nonmetal. So this would be a nonmetal bonding with a nonmetal, which is a covalent bond. And remember, the covalent bonds are all about trying to borrow each other's electrons through bonds to get the octet rule. It's not about balancing charges. There's no charges to balance. They both start out as balanced charges, so they don't need any help with that. Ions, they do need help with that. They're not balanced. But covalent, they're already balanced. That's not what they're needing help with. They need help with the octet rule. But what does happen is that once they are bonded in this covalent bond, the chlorine is so much more electronegative than hydrogen that it steals that electrical charge from the electron, from hydrogen's electron. It steals it and takes it for himself. Once that happens, it can break apart this molecule, and chlorine takes off with a stolen electron that it stole from the hydrogen, and hydrogen is left as just a proton with no electron because the chlorine stole it. So see, they turn into ions. Now this is an ion, now this is an ion, but that didn't mean that they started out as ions, and it didn't mean that it was an ionic bond. This was a covalent bond. It's just that once the electronegativity took over, it turned the covalent bond into 2 separate ions. And guess what this whole concept is? When it starts out as a covalent bond, but the electronegativity turns it into 2 separate ions because one steals the negative charge and goes their own merry way as an ion, and the person who got stole it from goes their own merry way as an ion, as a positive ion. This entire concept that I'm just telling you about is dun, 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 an acid. An acid. This is exactly what an acid is. An acid is, it's a covalent bond. It's a covalent bond between elements, but there's electronegativity comes into play, and it separates them as soon as they hit water. As soon as it hits water, it turns into separate ions. But it didn't start that way. They started as a covalent bond, not as ions. They both had their right amount of charges. They were both zero balanced. They were both completely balanced charges, no charges. But bonded together, the electronegativity and getting put into water dissolves them, and it's called dissociates. It dissociates, just which is a fancy term for separates. It separates these two into their ionic forms, and that is exactly what an acid is. Now, this entire deal about when something is partially positive on one side and partially negative on the other side due to electronegativity, and one stealing, whichever is more electronegative, steals the negative charge electron from the element it's bonded to, that makes this molecule polar. So this would be a polar molecule. This is a polar molecule. Water, as you heard, water is a polar molecule, and this is why, because the oxygen in the H2O sucks up all the electrons for itself, and so it's partially negative, leaving the 2 sides down here partially positive. So this is polar. So the electronegative movement turns the molecule into what we call polar, which brings us to acids. And not only are acids a covalent bond that dissociates into its ions, the whole reason why it dissociates into its ions, even though it started out as a covalent bond, is because it's a polar molecule. So it's a polar bond. So if we just had H, H, and H, these are all the same level of electronegativity. So nobody would be pulling electrons from anybody else because they're all the same strength. But the oxygen is way stronger than the hydrogens. So it pulls all the electrons up to oxygen. So that makes it more negative up here and more positive down here on these sides. So this is polar. Now you also need to, remember the basics about acids and bases, because this is going to be kind of helpful. Well, it's going to be kind of important to help you out in organic chemistry. Just remember, okay, besides what I just told you, that acids are a covalent bond that's polar, and the polarity separates it into ions. Okay, so remember that about acids, but also the definition, there's two ways of looking at acids and bases. See, depending on how you look at it. So you can either look at it that acids accept electrons because they have a proton to share. So they can donate a proton, or they can accept, and they'll put an or here, not both, but they can accept an electron or donate a proton. So either one of these things could be true if it's a base or an acid. It just depends on what you're looking at, what molecule you're looking at, what context it's in. And I think that's about it for what you should have been refreshing on, what you should be all caught up on and refreshed for to start studying mechanisms in your organic chemistry class. Next video, the part 2 video, I'm actually going to get into describing the components of the mechanisms and how they work on a basic level. If you do that next video before even starting your OChem class, you're going to be ahead of the game. So stay tuned for the next part of this video.